Hello guys, welcome back to another video on my channel. So this video is actually a direct continuation of the last video, which was the first Barnes lemma. In this video, I'm gonna do the second Barnes lemma. So please make sure you watch the first one before coming right onto this one, because there's many important details that we need, such as the region of convergence and the mellin transform and the inverse mellin transform. So, with that being said, let's get started. Okay, so we have the statement of the second Barnes lemma. We have 1 over 2 pi I times integral from minus I infinity to I infinity dz, gamma of alpha 1 minus z, gamma of alpha 2 minus z, gamma of beta 1 plus z, gamma of beta 2 plus z, gamma of beta 3 plus z, all of that divided by gamma of alpha 1 plus alpha 2 plus beta 1 plus beta 2 plus beta 3 plus z. And all that is equal to, now this is quite a mouthful, gamma of alpha 1 plus beta 1, gamma of alpha 1 plus beta 2, gamma of alpha 1 plus beta 3, gamma of alpha 2 plus beta 1, gamma of alpha 2 plus beta 2, gamma of alpha 2 plus beta 3 divided by gamma of alpha 1 plus alpha 2 plus beta 1 plus beta 2 times gamma of alpha 1 plus alpha 2 plus beta 1 plus beta 3 times gamma of alpha 1 plus alpha 2 plus beta 2 plus beta 3. Again, and all this has a condition such that the real part of alpha 1 plus beta j is greater than 0 for all ij, where I will be summed from 1 to 2 and j will go from 1 to 3. And when such a condition exists, there's a clear separation between the real part of alpha I and the negative real part of beta j, such that we can place a contour of integration between the real part of alpha and the negative real part of beta for all alphas and betas. And that's precisely what I'm doing. I'm placing the contour such that the real part of z, and z is the integration variable, it's the variable that denotes that we're on the contour, that is in that strip between the real part of alpha and the negative real part of beta. And just like the first Barnes lemma, we can actually weaken this condition to exclude the negative integers, so that the gammas don't really blow up anywhere. But this, in this form, it's pretty elegant, and you'll see why. There's things that are going to be working out nicely like they did in the first Barnes lemma. Okay, so first of all, let's recall the first Barnes lemma, because we're going to use that extensively. And I mean that when I say that. So we have 1 over 2 pi I times integral minus I infinity to I infinity dz, gamma of alpha 1 prime minus z, gamma of alpha 2 prime minus z, gamma of beta 1 prime plus z, gamma of beta 2 prime plus z. I'm using prime notation because we can do a substitution later, equals gamma of alpha 2 prime plus beta 2 prime, gamma of alpha 1 prime plus beta 1 prime, gamma of alpha 1 prime plus beta 2 prime, gamma of alpha 2 prime plus beta 1 prime divided by gamma of alpha 1 prime plus alpha 2 prime plus beta 1 prime plus beta 2 prime. And in this general form of the first Barnes lemma, I'm just going to relabel a few things. I'm going to call alpha 1 prime z, and alpha 2 prime to be alpha 1 plus alpha 2 plus beta 1, beta 1 prime to be beta 2, and beta 2 prime to be beta 3. Again, with the condition that the real part of alpha 1 prime plus beta 1 prime is greater than 0. And if you plug, whatever each of these guys are, you will essentially end up with the non-trivial condition: the real part of z is greater than minus real part of beta 1 and the real minus real part of beta 2, which in our case is satisfied. For the choice of z that we had, we are really satisfying that That's the given, that's the condition we have on the statement of the lemma. So that's a given, so that's really satisfied. We can check that box. And the variable of integration is actually going to be s now. That's why I could make this choice. And given such a split between the between z and the negative real part of beta 1 beta 2, we basically have to place our contour real part of s between alpha 1 prime and negative real part of beta j prime, which basically it just ends up being this, which is true because of this relation that we're satisfying, real part of z greater than minus real part of beta 1 comma beta 2. It's because of that we can really place the contour in the standard range, and we can actually apply Barnes' first lemma in this case. So we have 1 over 2 pi I integral minus I infinity to I infinity ds gamma of z minus s, sorry, gamma of alpha 1 plus alpha 2 plus beta 1 minus s, gamma of beta 2 plus s, gamma of beta 3 plus s, all that equals gamma of alpha 1 plus alpha 2 plus beta 1 plus beta 3, gamma of beta 2 plus z, gamma of z plus beta 3, gamma of alpha 1 plus alpha 2 plus beta 1 plus beta 2, divided by gamma of z plus alpha 1 plus alpha 2 plus beta 1 plus beta 2 plus beta 3. Now, this is one of the nice forms that we have here. We can use this in the place of the last two terms of the left hand side of the second Barnes lemma expression, divided by the denominator. We can use this integral relation to substitute for this. So what is this in the green? Well, that is actually just the last two terms of the statement of Barnes lemma. It's gamma of beta 2 plus z and gamma of beta 3 plus z divided by the denominator. It's the last two terms and divided by the denominator. It's just those. We can rewrite them in terms of this integral in s. So what's happening is there's an integral in z outside, given this condition that should hold. And then we're introducing an s integral inside by this substitution that we had here with the primes going on. That's because of Barnes' first lemma, and all of that holds because the real part of z is basically satisfying the initial assumption that we have. So using this, we can write gamma of beta 2 plus z times gamma of beta 3 plus z divided by gamma of z plus alpha 1 plus alpha 2 plus beta 1 plus beta 2 plus beta 3 to be, we can take these these other factors that don't depend on z and divide them out, and we get those factors up front, times the integral from minus I infinity to I infinity, which is basically going to be the left hand side in blue, ds over 2 pi I gamma of z minus s gamma of alpha 1 plus alpha 2 plus beta 1 minus s gamma of beta 2 plus s gamma of beta 3 plus s. And again, the conditions that we have from the placement of our contour, from this condition, negative real part of beta j prime less than real part of s less than real part of alpha 1 prime for all ij, that gives us, if we plug everything for alpha prime and beta prime, we get negative real part of beta 2 and the negative real part of beta 3, both are less than the real part of s, which is less than the real part of z. And the other condition is real part of s is less than the real part of alpha 1 plus alpha 2 plus beta 1. Now, the first condition implies the second. Because why? Because based on the initial assumption of this lemma, real part of z is less than real part of all alphas, right? So that's also real part of z is less than real part of alpha. And we know that that alphas, the real part of alpha, any alpha with any beta plus any beta is always greater than 0. So you're basically just adding, after alpha 1, you're just adding some some positive term. So that's why, this establishes just the real part of S being less than real part of Z establishes the second condition as well. So what this has done is we have this inequality minus real part of beta 2 comma beta 3 less than real part of S less than real part of Z, and that Z is less than any real part real part of any alpha. Okay, so that takes care of all alphas, alpha 1 and alpha 2 namely, and also takes care of the beta 2 and beta 3. The only thing that isn't taken care of automatically from this formula is the beta 1. So in the case that the negative real part of beta 1 is less than real part of S, we're good. We don't need to do anything else. But in the case that the negative real part of beta 1 is greater than the real part of S, then just choose S such that, it lies on the other side of all the betas. So choose S such that the negative real part of beta j for all j is less than the real part of S, less than the real part of Z, less than the real part of alpha I for all I. And that should basically, be the standard choice in this case. And you'll see how this will actually be really helpful for us. You see where the Z, real part of Z, is still satisfying the initial assumption we had. It's just that the real part of S is, being inserted in there. So now let's interchange the S and Z integral. So as I said before, we have two integrals. We had a Z integral outside because of the, the natural form of the left-hand side. And we introduced this S integral from application of the first Barnes lemma. So all we have to do is we have to, do the Z integral first by interchanging the order. So we have integral ds, integral dz instead of integral dz, integral ds. So let's just group all the terms with the Z. So the terms that recently got introduced, there was only one term with the Z. It was gamma of Z minus S, this term. So we take that and add those terms from before, which are going to be gamma of alpha 1 minus Z, gamma of alpha 2 minus Z, and gamma of beta 1 plus Z. And the other terms that's generated from, using Barnes' first lemma on the last two, beta 2 plus Z, beta 3 plus Z, is basically just gamma of Z minus S. So we can use Barnes' first lemma again with beta 2 equal to minus S. And with such a variable change, we can still satisfy this condition that we had. So, we can still use Barnes' lemma because we're still in that good choice, that strip, that region of convergence. And this is easily checked because that's how we chose S. Be between all the negative real part of betas and the real part of Z's. So all of this can be simplified. This entire Z integral can be simplified to give us gamma of alpha 1 plus beta 1, gamma of alpha 2 plus beta 1, gamma of alpha 1 minus S, gamma of alpha 2 minus S divided by gamma of alpha 1 plus alpha 2 plus beta 1 minus S. So the great thing is we're out of the Z dependence. We've completely evaluated the Z integral. So plug this back into the S integral because that's the one that needs to be done. So we have integral minus I infinity to I infinity ds over 2 pi I. So if we go back, this was by collecting all the Z terms. We left out the S terms, which did not have any Z dependence on them. So that's this term, gamma of alpha 1 plus alpha 2 plus beta 1 minus S, and gamma of beta 2 plus S and gamma of beta 3 plus S. In addition with the integral that we just have by doing the Z integral. So if we club all those terms, and I'm dropping all the prefactors from now on. So I've dropped 2 free factors here, and I will be dropping another one in the future. We can group them towards the end. So if you plug this back into the S integral, we have integral minus I infinity to I infinity ds over 2 pi I gamma of alpha 1 minus S, gamma of alpha 2 minus S, gamma of beta 2 plus S, gamma of beta 3 plus S, divided by gamma of alpha 1 plus alpha 2 plus beta 1 minus S times, conveniently, gamma of alpha 1 plus alpha 2 plus beta 1 minus S. Why convenient? Because it's exactly the same factor as in the denominator, and we can cancel that out. So from this, we can still use Barnes' first lemma for the last time. Why can we do that? Because we're still in the region of convergence. We're going to use Barnes' lemma for the alpha 1, alpha 2, beta 2, beta 3 poles. So minus real part of beta j less than real part of s less than real part of alpha I for all ij is still satisfied. And that was basically our choice for s. So we're good. Equals, just using the first Barnes lemma, gamma of alpha 1 plus beta 2, gamma of alpha 1 plus beta 3, gamma of alpha 2 plus beta 2, gamma of alpha 2 plus beta 3, divided by gamma of alpha 1 plus alpha 2 plus beta 2 plus beta 3. So you see there's additional prefactors now, and we're going to need to regroup them in this step. So the prefactors are the gamma of alpha 1 plus beta 2, gamma of alpha 1 plus beta 3, and the gamma of alpha 2 plus beta 2, and the gamma of alpha 2 plus beta 3, along with the gamma of alpha 1 plus alpha 2 plus beta 2 plus beta 3. And then there were all these other prefactors coming in, two of these, 1 over gamma of alpha 1 plus alpha 2 plus beta 1 plus beta 3, 1 over gamma of alpha 1 plus alpha 2 plus beta 1 plus beta 2, two of those, and the remaining ones coming from the the final form that we have here. So when we club that in, we basically just get the right hand side, because we started with the left hand side, which was this integral. We took the last two terms, used Barnes' first lemma on them, and chose a good choice for the real part of s, the s contour, the inner integral contour. Interchanged the z and s, did the z integral first, used Barnes' lemma once, solve that integral, use Barnes' lemma again, solve the final integral in s, and then just regroup the factors. That's it. This second Barnes lemma is basically an application of the first Barnes lemma just 3 times, and respecting the regions of convergence and choice of contours, especially for the real part of the integrating variable. And that's essentially the crux of this entire business with mellin transforms. It's just the region of convergence, not just mellin transforms, actually just integral transforms. Okay, so I hope you enjoyed the video. Apologize if there's any mistakes or any sloppiness from my side throughout this series. I promise in the next video we're actually going to use these nice results that we've just proven in this video and the previous one. So peace out, like, share, and subscribe to my channel, and see you next time.